Welcome to today's lecture on chemical kinetics. If you remember yesterday what we were discussing was we were discussing the temperature dependence of reaction rates. So, this is the topic we were discussing, and when we started our chemical kinetics and we were progressing through the lectures, we said that whatever rate laws and everything we were looking at or getting experimentally, they were always done at a fixed temperature. The reason being that temperature, reaction rates do depend upon temperature. That means temperature has influence on the rate of a reaction. Now then the next step was, is there a mathematical expression that can tell me how the rate varies as a function of temperature? So in that regard, the equation we are very familiar with is the Arrhenius equation. So this is what we had started with yesterday, at the last part when we were talking about the temperature dependence. So the Arrhenius equation goes as K, which is the rate constant, is equal to A, the pre-exponential factor, times exponential minus EA by RT, right. And then in the next few minutes we had talked about the relevance of this equation and what the different terms out there mean. Now the last part of this last class, we were focusing on, or we were trying to get an idea of how Arrhenius came up with an expression like this, right. And doing so, what we said was, we started with this Van 't Hoff expression. So we will just write again. We say that Van 't Hoff, in a famous book of his, used this expression, see, over del T at constant pre. So this Kc is your equivalent constant expressed in terms of concentrations, which we saw before. This is equal to delta U naught over R T squared, right. And we had given this an equation number of 2. After that we wrote down an equilibrium reaction A plus B going to P plus Q, and we said that okay, Kc can be written in the form of K1 over K minus 1. Okay. I am skipping all the intervening steps because we had done this in the last class. So please refer back to the last class lecture notes and discussion. Well, what is K1? K1 is the rate constant for the reaction in the forward direction, and K minus 1, as the minus sign is indicating, is a change in direction. That means K minus 1 is the rate constant for the reaction in the backward direction. So forward means A plus B going to P plus Q, and backward means P plus Q going back to A plus B. So now once we had this, what we did was, you see in this expression we had this Kc. So this was a partial derivative because we are taking it at constant pressure. This delta U is the standard internal energy change based upon the reaction. Okay. Now what we can do here is we can take this expression for Kc and put it back in this equation. So I will remove the partial derivatives, and then what I can write is d ln, this is now K1 over K minus 1 over d of t, right, is equal to delta U0 over R T squared. Okay. Now Van 't Hoff, what he said was, he argued, what he said was that okay, this K1 and K minus 1 would be related to certain energies E1 and E minus 1. So then Van 't Hoff says, or Van 't Hoff, I can say, argued based on his proposal or based on his proposed hypothesis that K1 and K minus 1 will be influenced by two different energy factors, which are E1 and E minus 1. Okay. So, these are the two energy factors, and based on this he could then write that d ln k1 over d of t is equal to E1 over R t squared d k, this is k2 over, sorry, I will not write k2, this is minus 1. So, please make sure that this is d ln k minus 1, which is the rate constant for the backward reaction, over d of t is equal to E minus 1 over R t squared. So, now again you can understand that this E1 is the energy factor associated with the forward reaction, and E minus 1 is the energy factor associated with the backward reaction. Okay. So, after that, what having said this, what he then did was, he said that okay, based on this, if I if I am able to write this, I should also be able to write that E1 minus E minus 1 is equal to delta U naught. Once you have all these set, then it becomes very clear. So, if you would integrate one of these equations, say for example, if you would just say d ln k over d of t is equal to E over R t square, and if you would integrate this equation, then what you will be getting is ln k. So, that means you can take dt over this side, do the corresponding integration, you will be getting is equal to constant minus E over R t, or now I can write, so this constant, it is a constant, this is logarithmic base E. So, you should be able to understand how we can write the next step, where I can write that k is equal to a e to the power minus E a over R t, right. So, this you should be able to figure out by yourself how from here to here I can write the same. But anyway, what it tells you is, it gives an idea of how this Arrhenius equation came about. So, let me see what the what the equation number was for this last one yesterday. Okay. So, then this one was, I think, equation 9, which we gave, right, and then obviously this is the Arrhenius equation. But then I am sure you are wondering right now, if Van 't Hoff had already proposed this, then why is it said it is the Arrhenius rate equation or the Arrhenius expression for the temperature dependence of the rate constant on how the temperature, how the rate constant depends on temperature, why we call that equation as Arrhenius equation, because Van 't Hoff had already given all these things. Now, the importance of Arrhenius is here. So, what did he do is, he generalized it. So, let us think about Arrhenius right now. See, again, from this hopefully you got a flavor that how this Arrhenius rate, Arrhenius expression for the dependence of temperature of a reaction rate or rate constant can be derived or can come into being. But then, as I was telling you, since it was already proposed by Van 't Hoff, why would I call it to be an Arrhenius equation? So, Arrhenius, he accepted this approach by Van 't Hoff, right, and he tried to generalize it. He said that this is possibly applicable for any possible reaction, but how does, or how did he visualize the reaction happening? This is what he proposed. So, what he proposed was that this is a general concept. This means the Arrhenius or the previous equation, which is k is equal to a e to the minus E a over R t. So, here you see I have replaced this E by E a, which is essentially our activation energy, This is a general concept of how reactions occur. Okay, it is a general concept. And what he said was, an equilibrium, like chemical equilibrium, an equilibrium is established. An equilibrium is established between normal and active reactant molecules. Okay. So, let me underline these two words. So, what Arrhenius proposed was, he said that this is indeed a general concept of the temperature dependence of a certain reaction or any given reaction, say, and in the process of giving an explanation for the expression you have seen, he said that an equilibrium is achieved between two types of molecules, reactant molecules. One is a normal reactant molecule and the other one is an active reactant molecule. Now, just merely by these two words, normal and active, you understand that he is creating a difference between the types of molecules which are present in your reaction system or the reaction vessel where you are carrying out the reaction. Normal reactant molecules means they are normal out there. Active reactant molecules, by the word active, means they are more active towards a certain reaction. Now, what we mean by that, what we mean by these active reactant molecules, we will soon see, but you must be realizing right now that he has been able to make a distinction between the two groups of molecules that are present in a reaction vessel at any given moment. One is a normal set of reactant molecules and the other one is an active set of reactant molecules, and it goes without saying that it is the active set of reactant molecules which would finally go over to the product side and actually give you the products, right. That is why they are called the active reactant molecules, because they are active enough so that they can give rise to products by whatever changes that happen in the reaction. Okay. Now, see, Arrhenius, he received his Nobel Prize for his theory of electrolytic dissociations, right. So, he did not receive Nobel Prize for this this thing, the temperature dependence of reaction rates, and he was working on few reactions. One of the reactions he was working on was the inversion of cane sugar. Okay. So, one of the reactions Arrhenius was working on was the inversion of cane sugar, right. And here he said that during the inversion process, the inversion was not brought about, the inversion was not brought about by a simple cane sugar molecule. It was not brought about by a simple cane sugar molecule, but a substance he referred to, or he mentioned as active cane sugar molecule, but a substance he mentioned as active cane sugar molecule or active cane sugar. And it goes without saying that the rate of this reaction or the rate of a reaction is proportional to the concentration of active molecules. So, if I write, then he said that the rate of reaction is proportional to these active cane sugar molecules, right. So, this introduction of this word active was a key step taken by Arrhenius in his proposition or in his generalization of that rate expression k is equal, or that expression k is equal to a e to the minus E a by R T. Now, let us try to draw a schematic profile, to understand what we mean by this. So, let us start from a very simple schematic profile. So, here on the x axis I have something known as reaction coordinate. On y axis, so this is my reaction coordinate. On y axis what I have is something known as potential energy. So, on the x axis I have the reaction coordinate, on the y axis I have the potential energy. So, if this is my reactant, say this would be my reactants, products, right. Then on my way from reactions to products, this is how the potential energy profile should look like. Okay, so this is how the potential energy profile should look like, right. So, what you are seeing out here is I have my reactant out here, I have my product out here, right, and on my way from the reactant to the product, if you remember the equilibrium equation we are talking about, what we can say is, say if I take this maximum, this one can be labeled as E1, right. Then if I extend this line on the other side, then I can say from here to here, this is E minus 1, right. Then the difference out here between the reactants and the products is your delta U naught. What is the general form of this expression, or rather this plot, what does it say? So, you have reactants, you have products. So, the relative energy levels will depend upon what type of reaction you are looking at, right. The difference between the two potential energies, that means the potential of the reactant and the potential of the product, is equal to your change in internal energy, that is the standard internal energy, right. Now, when the reactant has to go to the product, what happens to the potential energy is, you start from the potential energy of the reactants, then you slowly move upward, right. Then you reach a maximum. Once you reach the maximum, once you go over to the other side, so this is the maximum, right. So, this is the maximum of the potential energy. Once you go to the other side, then you can again see that the potential energy started to decrease, hence you come down to the products. So, then for the reactants to go over to the product side, they have to surmount an energy barrier which is given by E1, okay. So, this E1 is the energy barrier. On the other hand, if the products have to come back to the reactants, they have to surmount an energy barrier which is given by E minus 1, and as again I said before that E1 is the energy associated with the forward reaction and E minus 1 is the energy associated with the backward reaction. So, this E1 or E minus 1, or let us say E1, because we are more accustomed to looking at reactions going from reactants to products. So this E1, this E1 is your EA, the activation energy. Okay. So this E1 is equivalent to EA, the activation energy. We will talk about this more when we go to the next topic, which is about elementary reactions, about looking at a schematic energy profile and see what information it gives us. But for the time being, it is enough for us to understand the bare essential features of a certain plot like this, where if you have to go from the reactant to the product side, you have to go up in the potential energy, right, go to a maximum. Once you reach the maximum, then you make a transition over to the product side. So this state out here, is called the transition state. So if I write, if I say there is a state out here, then I can say this is my transition state. So what does this mean? That means this is a state through which I transition from my reactants to products, and that is why it is called the transition state. And obviously the way it has been depicted on the diagram, the transition state is the one which is at the top of your potential energy, that means having the highest energy. So the moment you move on two sides of the transition state, what happens is your potential energy diminishes, right. So if you are going from here to here, the potential energy increases to the transition state. Now the moment you go to the other side of the transition state, what is happening is now you are going to the product side. So again the potential energy starts decreasing because your products have started forming, right. But in between there is an energy barrier which the reactants will have to surmount to go over to the product side, and this energy barrier essentially is given as your activation energy, which is EA, right. Okay. Another thing is, if you look at your books, even a NCERT book or some other books, you will see that this difference in reactants and products, instead of del U naught being written, it is it's many times written as del H naught. But do not worry, it is not a problem at all. So let us look at what I mean. So remember, we are focusing on del U naught right now. So think about this. We know this from thermodynamics, that H is equal to E plus PV, right. Then once I have this, I can write that if I have a finite change in delta in the enthalpy H, so where H is the enthalpy, okay. So I used another, let me rewrite this, hold on, just let me rewrite this, let me take another sheet of paper. You will soon understand why you need to rewrite. So I am saying del or H, your enthalpy, is equal to U plus P V, right. So your enthalpy H is equal to U plus PV. In the sheet before, I had written E, but E is also used for symbolizing internal energy, but then I was using E for my activation energy, so you might get confused. So I came back and used E, because this was what I also used for depicting this difference between the reactants and the products, the potential energy difference, right. Okay. Now remember what we had started with. What we had said was that you should not be confused by the fact that there is whether delta U naught or delta H naught, because now if I look for a finite change in H, then this would be equal to delta U plus delta P V. This can be rewritten as delta U plus P delta V plus V delta P, right. So this is delta H. Okay. Now suppose if you would remember that this d ln Kc over dt, which I had written it as a partial derivative, right, initially. So it was del ln Kc over del T at constant pressure P. So because it is constant pressure, then del P should be 0. So let us now rewrite this then. So I can write again delta H is equal to delta U plus P delta V plus V delta P. Now, at constant pressure, delta P is equal to 0, which means this is equal to 0. So, the moment I write that, then I have delta H is equal to delta U plus P delta V, right. Now, for reactions in condensed phases, that means for reactions in solids or solid state and solutions, the volume change is very small. We know this, right, that the volume change is very small. So, we can write delta V is almost equal to 0. Hence, for solids and solutions, right, or liquid state, we can write that delta H is equal to delta U. So, now go back to what we had started discussing this from or about. So, we are talking about this delta U naught, then for solids and liquids or solutions where reactions are happening in solutions, then we straight away have this delta U naught is equal to delta H naught, no problem, right. But what about gases? Gases, I cannot say this, okay. So, let us talk about gas phase reactions, right. Again we start from delta H is equal to delta U plus P delta V, right. Now, remember we had said that pressure was the constant, right. Let us consider ideal gas behavior for the gas molecules, okay. Now, starting from the ideal gas equation where P V is equal to N R T at fixed temperature and pressure, I can write P delta V is equal to delta N R T. See, it is very simple, right. I was looking at this P delta V factor out here, right. For ideal gas, P V is equal to nRT. Now, I have taken the conditions where my pressure is fixed and my temperature is also fixed. So, if I am looking at a change in this equation, P is not going to change because P is fixed, T is not going to change because T is fixed, R is a constant, it is not going to change, right. V, I have replaced V by del V now, because del, volume can change, obviously will change in case of gases. And then this change in volume is equal to delta N RT, right. So, what we can do now is we can take this P delta V is equal to delta N RT and use it back in this equation, right. Using this, what are you going to get? We are going to get is delta H is equal to delta U plus delta N RT. What is delta N? So, delta N is the change in number of moles as you go from the reactant to the product side. So, under conditions where if delta N is equal to 0, so if delta N is equal to 0, then immediately you understand that delta H is equal to delta U, right. So, again going back to what we started from, remember. So, for delta N is equal to 0, this straight away comes out to be delta H naught. Now, even if delta N is not equal to 0, what will happen is, see R and T, these are constants, right. So, then this delta N gets replaced by 1, 2, whatever, and still you will be having a working relation between what delta H and delta U. So, that means if it is say delta n is equal to RT, then delta U can be replaced by delta H minus RT and so on. So, that is why you do not have to be bothered by the terminology I used here, right, rather the thermodynamic parameter used here to describe the potential energy difference between the reactants and the products, because for solids and liquids it is no problem. For reactions happening in the solid state or liquid state, the solution state, this is always equal to delta H naught at constant pressure, because first of all reactions are generally observed at constant pressure, and secondly the volume change for these systems, that solids and liquids, are so low that the delta V essentially is equal to 0, right. However, in case of gases, as that is what we were considering, we can always say at fixed T and P we have P delta V is equal to delta n RT, and then go forward and say that okay, if I have delta n is equal to 0, then delta H will be equal to delta U. If delta n is not equal to 0, then still I know that delta H is equal to delta U plus delta n, which will be having some value times RT, and then I can always replace delta U by this delta H. Okay. So, that is how you relate these two things. Okay. Now, based on a discussion of what we were doing out here, let us try to look at this activation energy again from a different point of view. So, the point of view is the following: suppose there is a system having 1 mole of gaseous reactants. Okay, 1 mole of gaseous reactants. Now, 1 mole is Avogadro's number, it is 6.023 into 10 to the power 23 molecules. Now, the question is, at a certain temperature the molecules will be having their own kinetic energy, go back to this kinetic theory of gases. Okay. So, molecules will be having their own kinetic energy, but by think about this, if I have a certain temperature, say T is equal to 300 Kelvin here, which is close to room temperature, would you expect each and every molecule, that means each of these 6 point this 10 to the power 20 molecules, would each molecule have the same kinetic energy? Probably not. So, what happens is that when at a certain temperature, certain temperature, and I am talking about gaseous reactions, it goes back to the kinetic theory of gases, right. You must have done this in some other class. So, at a certain temperature what happens is that all molecules in the system do not have the same kinetic energy. Okay. So, they do not have the same kinetic energy. Instead what happens is you have a distribution, that is a distribution of kinetic energies, exist in the system, and this distribution depends on temperature. So, this is important, this distribution depends upon temperature. Now, even before showing you the distribution, we'll not look at very much details of the distribution, what the equation the distribution is based on and so on. I'll just show you the distribution so that you have a feeling of what this Arrhenius equation is all about, what this activation is all about and so on. Okay. Now this distribution, it says it depends on temperature. Now this is obvious, right? First, let's not worry about the distribution. If I have a certain temperature, say 300 Kelvin, the kinetic energy say is E1. Now if I increase the temperature to 600 Kelvin, obviously the kinetic energy is going to increase, right? But now the difference is that I am not talking about one molecule, because I have made this statement in this previous sheet of paper, that at a certain temperature a system having this many molecules or having so many molecules, not every molecule would be having the same kinetic energy, hence there will be distribution obviously. Now on the other hand, if I increase my temperature, that means I change my temperature, I will also change my kinetic energy. If I change my kinetic energy, then I am also going to affect my distribution of kinetic energies. And how is that? But first let's take a look at the distribution of kinetic energy. So this distribution was first proposed by Maxwell and Boltzmann. The distribution was proposed by Maxwell and Boltzmann, through a series of equations that they derived. So this is how the distribution looks like. So this is kinetic energy. Okay. So this is kinetic energy. So this on this side will be fraction of molecules. Okay. And how will the distribution look? So this will look like this. So this is how the distribution looks like. Okay. Now, so you have kinetic energy on the x axis. I will just tell you what I mean by the fraction of molecules, right. I will tell you right now, but see an important feature of the distribution. One, it is a distribution, so there is a finite width, it is not a single line, it is a finite width. What does it mean? That means you have a range of kinetic energy starting from almost 0 to the other side, right. So this is the distribution. Somehow in between, somewhere in between, the kinetic energy value peaks. So that means there will be a fraction of molecules having the maximum kinetic energy, right, and that is where the fraction of molecules is peaking. So which means that at this value, so if I say this, okay, and I also extend on this side, you can see that the fraction, because there is a fraction, the fraction is also high, the highest out here, the fraction is maximum, and here the kinetic energy is also maximum, right. Then we say that this value of kinetic energy corresponds to the most probable kinetic. It corresponds to the most probable kinetic energy. Why is it most probable? Because you understand that the maximum fraction of the molecules is having this kinetic energy, and hence it is called the most probable kinetic energy, right. But again see that it is not one line, but it is a distribution having a finite width. That means at this temperature, say this is T is equal to 300 Kelvin, in my system having this many molecules, not every molecule is having exactly the same kinetic energy. There is a distribution of kinetic energies spread over this range. Not only that, the distribution also peaks at a certain point. This peak, to be read off from the y axis, corresponds to the maximum fraction of molecules having this kinetic energy, and because the maximum fraction of molecules is having this kinetic energy, it is called the most probable kinetic energy, because the maximum fraction of molecules is seen to have or possess this most probable kinetic energy. Okay. we will come back to a comparison again where we will take a higher temperature and see how this distribution changes, because whatever we are doing is we are trying to understand this Arrhenius equation, right, in a much better way, trying to have much deeper insights as to what might be happening as you change the temperature. Okay. What about this fraction? So, the fraction is this. So, that means you say that okay, suppose the total number of molecules is n in the system. If the total number of molecules is n, right, then you have a certain fraction. What is that fraction? So, the fraction is n e by n. The fraction is n e by n. So, what is n e? Say n e is the number of molecules having kinetic energy E, that is why it is called Ne. And as we had seen before, the peak of the distribution, the peak of distribution, it corresponds to the most probable kinetic energy, okay, which I am abbreviating by Ke. So, the peak of the distribution corresponds to the most probable kinetic energy, and this is Ne, which is the number of molecules having certain kinetic energy E. So, again you go back, and if you think about the fraction Ne by n, then it just tells you that this point I have the maximum fraction, that means I have the maximum number of molecules which is giving me this value of kinetic energy, and because the maximum number of molecules is giving you that value of kinetic energy, hence that kinetic energy being read off from the x axis corresponding to this fraction is called the most probable kinetic energy, as simple as that. Great. Now, having understood that there is a distribution of kinetic energies, and that is that the distribution peaks at a certain point which is called the most probable kinetic energy, let us see how this distribution varies as I change temperature. So, let us look at that now. So, again out here I have the reaction coordinate, and this again like before is my fraction of molecules. Now, let us take two temperatures, and it does not matter what temperatures they are as long as the two temperatures are different. So, for example, let us take a temperature which is a distribution like this. So, let this temperature be T is equal to 300 Kelvin. Okay. Now, let us take another temperature. This time this temperature is higher than 300 Kelvin, and say the temperature is say 600 Kelvin. So, now what happens, you see so let me take a higher temperature. So, let this temperature be, so let this temperature be equal to say 900 Kelvin. Now, what has happened? Two things. One is that from here to here, when I change the temperature, the distribution has become very broad. Not only that, my peak which was here, the most probable value peak which was here has actually gone to somewhere So this is, so the most probable kinetic energy has increased at a higher temperature as compared to that of 300 Kelvin. So 900 Kelvin I have a higher value of most probable kinetic energy as compared to that of 300 Kelvin. Again please realize that this has not been drawn to scale, but just to make the point, now remember I had this activation energy, okay. So let me draw a line where I say, so let me draw a line and I say that this kinetic energy, I did a mistake, I am sorry, this is not my reaction coordinate, I am still in that mode. So this is as we had showed, this is my kinetic energy, extremely sorry for that, please make that change, this is my kinetic energy, right, not my reaction coordinate, okay. Anyway, coming back to what I was telling you, that here what does this line mean? This line corresponds to EA. So this is EA, my activation energy, right. Now for the reaction to happen, the molecules have to have this activation energy so that they can go over the barrier, that means the top of this potential energy surface or the potential energy, and go to the product side. So the minimum energy that these molecules need to possess to go to the product side is EA. So any energy which is higher than EA, so that means any molecule having energy higher than EA would be able to go over to the product side, right. So let me shed that portion. So for the first curve 300 Kelvin, you see that the shaded region is the number of molecules, right, which are having, or the fraction, total fraction converted to the number of molecules having energy higher than EA. So this point they would, if they are having this energy higher than EA, then they would definitely go over to the product side. Now for the same reaction, considering the fact that when I go to 900 Kelvin the EA has not changed, that means the activation energy is say temperature independent. Now if you make the shade, trying to make it a different color, you see what will happen is the shade, you see you will be having a much higher population. So when I was at 300 Kelvin I was only looking at this blue shaded region, when I am at 900 Kelvin I am looking at the shaded region which is this plus obviously the blue ones, right, because they also fall under the distribution, and it immediately tells you that when I have increased my temperature, I have gone higher up, the fraction of molecules having energy greater than EA has also increased correspondingly, okay. So the few points that I should remember from this discussion is, when I raise my temperature from 300 to 900 Kelvin, my distribution becomes broad, right. When my distribution becomes broad, along with that there is a shift of the peak value, which is the most probable value of kinetic energy, to a higher value. Now this is logical, why? As I was telling you before at the start of the discussion of this distribution, that if I increase my temperature, then obviously my kinetic energy is going to increase, right, and hence this is reflected by the shift of the peak from here to a higher value, right. Now we said that okay, I know that based on our profile, which was let me see whether I can get that, based on this potential energy profile we had drawn before here. So based on this potential energy profile, for the reactants to go to the product side, they need to surmount this energy barrier which is given by EA, the activation energy. So that means activation energy is the minimum energy that these reactant molecules need to possess to go over to the product side, right. Now when I take this and come back here and I say that okay, say my activation energy is somewhere out here EA, right, then any energy greater than EA means that all those molecules having that value of energy which is greater than EA must go over to the product side. Similarly, when I increase my temperature, what happens is the fraction of molecules having energy higher than EA has also increased. Because my fraction of molecules has increased, it immediately tells you that I have higher fraction of molecules and hence the rate will also be higher, and this higher fraction is given by what? By the shaded regions that I have under these individual distributions. I hope I have made myself clear. I will just jot down the few points that I said. So, then what happens to the distribution as temperature is increased? What happens to distribution as increased? So, 1, the distribution becomes broader. 2, the peak of distribution shifts to higher value of kinetic energy, right, and 3, this is possibly the most important thing, the shaded portion which shows the fraction of molecules having energy more than EA, the shaded portion which shows the fraction of molecules having energy more than EA, that area of shaded portion increases as the temperature is increased, and it can be shown. So, if I area increases as the temperature is increased, and it can be shown that fraction of molecules having excess energy, that is energy in excess of EA, is given by EA over RT, and then you can relate to the Arrhenius equation K A e to the power minus EA over RT. Okay. I will stop here for today. Hopefully, by having this discussion, I have been able to tell you, or show you the insights of this Arrhenius rate expression, or Arrhenius expression for temperature dependence of rate constant, and why it is called so after Arrhenius, because he proposed all these things and they do turn out to be very true. Okay. So, in the next class what we will do is I will finish off the rest of this chapter on I mean rest of this section on temperature dependence and move on to elementary reactions. Okay. Thank you.